Good morning, friends. In the last video, we discussed the chemical properties of halogen derivatives. Now today we are going to discuss about the optical isomerisms in halogen derivatives. Last year we studied about the isomerism. Isomerism is the two or more compounds having same molecular formula. When two or more compounds having same molecular formula, that phenomenon is called as a isomerism. This isomerism divides into two groups. One is called structural isomerism and second is called stereoisomerism. So last year we discussed about the structural isomerism. Now today we are going to discuss about last year we discussed about the structural isomerism. Now today we are going to discuss about the stereoisomerism one. In stereoisomerism we can say that the two or more compounds are there, then their structure is same. Their structure is same, only we can say that the arrangement of the atoms are different one. When the arrangement of the atoms are different, then it is called as a stereoisomers. That phenomenon is called as a stereoisomerism. This stereoisomerism divides into, again we can say, two, that is the geometrical isomerism and optical isomerism. So today we are going to discuss about the optical isomerism. That also we have to see about this isomerism, optical isomerism in the halogen derivatives. Let us start with now optical isomerism in halogen derivatives. So there are some basic concepts are there. So first we'll see some of the concepts in this. First about ordinary light. This ordinary light is there. This we can say white light that we are getting from sunlight also you can say, or any white light you can say that. Now you know that the white light is composed of the 7 different colors. So the light we can say, the rays coming out from that light, we can say that the vibrates in all directions, and then when these vibrations are, we can say that or these oscillations are there, this take place in all directions and they propagate perpendicular to the propagation of the, we can say that this light one. Means this light is there which travels, or we can, these rays travel, their oscillations travels which are perpendicular to the propagation of light. Then that light is there which contains we can say different colors one. It means it has the different wavelengths one. A white light, or we can say that the ordinary light, has the, we can say that the rays of different wavelengths and they oscillate in different directions which are perpendicular to the propagation of light. That is a white light, or you can say ordinary light. Now if you take suppose any color, suppose if you are taking yellow color or red color light, then that light is there, it is called as a monochromatic light. Means we can say that a ray of light which contains only single wavelength. In ordinary light there are the different wavelengths are there. The light rays having the different wavelengths and they oscillate in which are the perpendicular to the propagation of the light. In case of the monochromatic light, when we say monochromatic light, mono means one and chroma means we can say wavelength. A light which has only single wavelength, it vibrates in all directions and it, we can say, oscillate perpendicular to the direction of propagation of light. This light also we can say that the oscillate one. It oscillates in all directions one and it is perpendicular to the propagation of light. Then that light is there, it is called monochromatic light. Now see what difference is there. In ordinary light there are the, we can say that the rays are there of different wavelength, they oscillate in all directions one and perpendicular to the propagation of light. In case of the monochromatic light, there is the light of single wavelength, the rays of single wavelength. Okay, either you can take any one color, out of 7 color you can choose any one color and its, we can say, the rays are there, that is also we can say oscillate in all directions one and they are perpendicular to the, we can say that the propagation of light. That is the monochromatic light. Now, this monochromatic, this ordinary light, when it passes through the, we can say that the some solutions, for example, we have taken about the glucose solution one. Then what happens? This light is there, which is, we can say, ordinary light, which oscillate in all directions one. Now what happens after passing through that solution? It oscillates only in one direction. Suppose there's a diagrammatically I will show you. Suppose this light is there, it is an ordinary light. If it vibrates, it oscillates in all directions like this. It oscillates in all direction one. When this light is passes through the, we can say, in the Nichols prism, it is called as a Nichols prism. When it oscillates into the, we can pass it through the Nichols prism one. That time what happens? This light is there. It, we can say that it oscillates only in one direction. That is perpendicular direction like this. So when after passing this, we can say that the light, this ordinary light through this Nichols prism, that time it oscillates in only one direction. Here it oscillates in all directions. Here it oscillates only in one direction. Then this light is there, which is coming out to this Nichols prism one and vibrates only in one direction. This light is called as a plane polarized light. So ordinary light, it is a, we can say, light of the different wavelength one. When this light passes through the Nichols prism one, then it vibrates, we can say that in one direction one, and this light is called as a, we can say that the plane polarized light. Now this plane polarized light, when it passes through the, we can say that the certain solution. For example, we have taken here suppose sugar solution one. Sugar solution, or we can take the glucose solution. So what happened here? It passes through the, we can say that the sugar solution. That time this light is there. It rotates. Either we can say that the clockwise or anti-clockwise. It may rotate. We can say that the clockwise, or we can say that the anti-clockwise. When it rotates clockwise or anti-clockwise with the same angle. It may rotate, we can say, clockwise with some angle, or it may rotate, we can say that the anti-clockwise with the same angle one. Any one we can say that. That time we can say that that property is there which rotate the, we can say that the plane polarized light to the clockwise or anti-clockwise direction with the same angle. Then that property is there, which is called as a optical activity. I will repeat it again now. Ordinary light, it is a, we can say, light of different wavelengths, where the rays are there, they vibrate, they oscillate in all directions one, and they, we can say that their oscillations are there, they are perpendicular to the propagation of light. Now this light is there, when passed through the, we can say that the Nichols prism one, that time it vibrates only in one direction. So this light is called as, we can say that the plane polarized light. And when this plane polarized light passes through the, we can say, sugar solutions or glucose solution one, that time that light rotates in clockwise, or we can say anti-clockwise, right side, or we can say left side direction one, and with the same angle. Then this light is there, this property is there of rotating the plane polarized light to the right direction or left direction with the same bond and same angle one. Then that property is called as a optical activity. Now further, the substances which shows, we can say that such a property which shows this phenomenon optical activity, that compounds are called as a optically active compounds. They are called as a optically active compounds. And in that, suppose those who are, we can say that rotating the light to the right direction, those who rotate the light to the right direction, they are called as a dextrorotator. They are called as a dextrorotator. And those who are, those compounds, those who are rotating to the light to the left side one, left direction one, or we can say anti-clockwise directions, they are called as a levorotator. Now this dextrorotatory, also called as a D isomer or also called as a plus isomer. While levorotatory are there, it is called as a L isomer or minus isomer. So these are the notations. These two are, we can say that the notations of the dextro and levorotatory isomers respectively. So let us see what is given in this. We can say that this optically active compounds. Optically active compounds are there, and they rotate this, we can say, plane polarized light to the either right side or we can say that the left side one. That compounds are called as the optically active compounds. The optically active compounds which rotate the light to the clockwise direction, okay, that we can say that into the right side direction one, they are called as a dextrorotatory, also called as a D isomer or plus isomer. And the optically active compounds which rotate the plane polarized light to the left direction one or anti-clockwise direction one, they are called as a levorotatory or also called L isomer or minus isomer. Now, why these compounds are, we can say, showing such a property? Not all the compounds are. Only we can say that there are some compounds are there, they shows, we can say, this property one. They are rotating the, we can say, light one, which they show the optical activity one. It is because of the, we can say that they have the asymmetric carbon atom. Now, asymmetric carbon atom means, we can say that that compounds are there, they have the asymmetric carbon atom. For example, we'll take the example of the, we can say that this lactic acid. Suppose, sorry, we have started with the, we can say, halogen derivatives. So better we'll take the example of the, we can say, alkyl halide only. We'll take the example of 2-chlorobutane. Now this 2-chlorobutane, I will write the structure over here. Now this 2-chlorobutane, it is CH3, C, here Cl, and here I will write H, here CH2, CH3. It is, we can say that according to IUPAC name, the second carbon bears the chlorine one, so it is, we can say that 2-chloro, and here 4, we can say that the carbon atoms are there in a chain, so it is called as a 2-chlorobutane. In 2-chlorobutane, the second carbon is there which bears the, we can say that the chlorine one. If you see this carbon, now if you see suppose first carbon, the first carbon has the, we can say, 3 hydrogen atoms and 1 carbon atom. If you see second carbon atom, second carbon has 1 chlorine, 1 hydrogen, 1 CH3, 1 CH2. If you see third carbon, it attached to the, we can say that the 1 carbon, it is a CH, 2 hydrogen and 1 CH3. Similarly, fourth carbon and first carbon, so you see 3 hydrogen and we can say that 1 carbon. If you see only carbon number 2, which has all the 4 bonds with the different groups, it means here carbon, it forms the bond with the hydrogen, here it forms with CH3, that is carbon of CH3, here we can just see the carbon of CH2. All the 4, we can say that the atoms or groups are different ones. So this carbon is there, it is called as a asymmetric carbon atom. So the compounds which has the, we can say that the asymmetric carbon atom, they shows this optically active optical activity one. So when we are finding, suppose when we are saying that these compounds contain the optically active carbon one, it means this compound is called as it has a chiral center. So this point is there, this carbon is there, which are shown with the asterisk mark, that is called as a chiral. This compound is called as a chirality. Now there is one more property is there. Now suppose if you take its mirror image one, if you take its mirror image, what you will get here? You will get CH3, CH2, C, Cl, okay, and then here we get suppose here the CH3, here we get the hydrogen. Now if you see both this structure now, Both the structures are same. You know, 2-chlorobutane consists 2-chlorobutane only. But what difference is there? See, if you try to keep both the, we can say that the compounds one above the other, then they are called as a non-superimposable. They are called as a non-superimposable. Non-superimposable images of each other. See, suppose if we see the our palm in the mirror, it looks like this. If you try to keep like this on one above the other, they do not fix on each other. So these palms are there. One palm is mirror image. Both are the, we can say that the non-superimposable images of each other. When it is fixed one, suppose I would say the suppose one bowl is there. If you see mirror image, it becomes same, and then we can say that they are the superimposable images of each other. If it is spoon, its mirror also will be same spoon, means it fixed with each other. It is called superimposable images. Non-superimposable images means what here? It cannot, we can say that the fix one above the other. So here these two palms are there. If you try to keep one above the other, they do not fix each other. You can see that the thumbs which are not, we can say, one above the other one. Even you see fingers also, they are on the different way, we can say that. So here these are the non-superimposable images. Like this, here also when we are saying about the chirality or asymmetric carbon atom, these two images are there. This chirality and its mirror image both are the non-superimposable images of each other. So this property makes them, we can say that the optically active one. Now you can say that one of the compounds, suppose this first chirality compound, you are seeing the first compound, if it shows the dextrorotatory, its mirror image will show the levorotatory. If suppose we are saying about this mirror image dextrorotatory, then it will be, we can say that the levorotatory. So dear students, we have finished, we can say that the optically activity of the, we can say, halogen, the ability to work. So from today onwards, after the lecture, I will just give you about the, we can say, some assignment to you. Now what you have to do, just you find out the IUPAC names of the alkyl halides. It was there last year one. So you go through the textbook one. In the textbook also, we can say that the some activity based questions are there. In that they are the, we can say, IUPAC names. So write those IUPAC names which are asked, which were given in the last year's 11th standard, we can say, textbook, as well as now this year's, we can say, 12th standard book one. And you have read the IUPAC names of the different alkyl halides. One more thing, one more question you have to, you have to make the note on that. That is about the classification of the, we can say that the this compound.